Hello everyone, welcome back to our channel. We were discussing about relations and functions. A few general types of general type of functions is what we discussed in the last class. Today we'll continue with it. We were left with signum functions and greatest integer function. Now, what is a signum function? A signum function is usually defined as mod of x upon x for x not equals to 0 and f of x is equals to 0 for x is equals to 0. That means if you place the value of x as this is equals to y. So if you place the value of x as any value except for 0, you can place it over here and get a specific value of y. But if you place x is equals to 0, you'll get the value as 0. So for x is equals to 0, y is equals to 0. Let's see what values of f of x do we get if we place positive values and later negative values. So for x greater than 0, for all positive values, x is equals to 0 and x less than 0. Three conditions, three different regions or intervals. For x is equals to 0, your f of x is 0, already well defined. For x greater than 0, that means for a positive value, your equation is f of x is equals to mod x upon x. For positive value of x, numerator will be positive and denominator will also be positive. So if you have a positive value in the numerator and positive value in the denominator, your answers will also be positive. So for x is equals to 1, mod 1 upon 1, you'll get 1. For x is equals to 2, mod 2 upon 2 is equals to 2. So whatever value of x you're placing over here, you're getting the same value of x. So this can be written as x. This is mod 2 upon 2, which will be equal to 2 upon 2. 2 will get cancelled and you'll end up with 1. If you place x is equals to 3, mod 3 upon 3, which is 3 upon 3, and again you'll end up with 1. So no matter what value of x you place, you always end up with 1. Now, what happens if you place a negative value over here? The numerator is in terms of mod, so definitely the numerator will always be positive. But if you place a negative value, your denominator becomes negative, which means you're getting a negative value. Numerator will be positive and denominator will be negative, giving you a negative value when your x is equals to negative. With examples, let x is equals to minus 1. Mod of minus 1 upon minus 1. The numerator's negative value got converted into a positive value of 1. Denominator's negative value remained as it is, leaving you with minus 1 as its result. For x is equals to minus 2, you get mod of minus 2 upon minus 2, which is 2 upon minus 2, which will be equal to minus 1. So no matter what value of x you place, as long as x is negative, you'll always get a value of minus 1 over here. So with these examples, we understand that x value, your f of x value, f of x can only hold three values, plus 1, minus 1, or 0. So let's draw it on the graph. For x is equals to 0, y is equals to 0. For x is equals to 1, 2, 3, 4, all positive values, your y will always hold a value 1. So we can draw it by a straight line. For x is equals to negative values, your y will always hold a minus 1 value. So this is again a straight line. This is the graph for signum function. Now observe that for x is equals to 0, here you're getting 3 points. This one, y is equals to 0, y is equals to 1, and y is equals to minus 1. This is 1, this is minus 1. So for x is equals to 0, you should only get the value of 0. We represent this by a knot and this by hollow points. To give us a clear idea that at x is equals to 0, your y value will always be equal to value of the knot. The knot is 0. So for x is equals to 0, y is equals to 0. The closed circle is knot and the open circle is a hollow point. We sometimes called it as a dot and hollow circle as well. The next type of function is Okay, we forgot domain and range. So for here, domain will be all values of x. So domain is a real function, real set. What about range? No matter what values of x you place, you always end up with three values, 1, 0, and -1. We have a habit of writing values or elements in the decrementing order or from left to right. Any sequence of elements will suffice, but we prefer a descending order. No, sorry, we prefer an ascending order, an incrementing order. So domain is R and range is -1, 0, or 1. Codomain, since we are considering real functions, will be R. So your function f is defined from R to R domain, R codomain, and you end up with a range of -1, 0, and 1. Next, greatest integer function. Greatest integer function, again we are defining f over R to R, real value. Your domain is real, your codomain is real. Let's understand what greatest integer function is and calculate its range. Greatest integer function is also shortened as GIF, the first alphabet of the three words, GIF. It's represented by, its equation is f of x is equals to box x or square x or GIF x. This symbol, it looks like a square brackets. Its meaning is that square bracket of x is equals to greatest integer less than or equals to x. Let's understand this with respect to some examples. You can take random values of x, positive, negative, and so forth. Let's consider x to be one positive value, 1.1, one negative value, -2.5, and say a random value, 3, a whole number. You can also take -3, no issues. So x is equals to -1. Your f of x will be equal to box of 1.1. Here your f of x will be equal to box of -2.5. And in the third scenario, f of x will be equal to 3, box of 3. This value is equals to greatest integer less than or equal to x. So let's draw a number line. Let's understand where do we have 1.1. This is your 0, this is your 1. Here you'll get somewhere 1.1. Greatest integer, it has to be a greatest integer, leaving that aside, but the integer has to be less than or equal to x. So which integers are less than or equal to x for 1.1? On the number line, it will be 0, 1, -1, -2. All these are integers. Amongst these integers, you have to choose the biggest or greatest integer. Greatest integer less than or equal to x. So among these integers, 1 is your greatest integer. Hence, f of x is equals to box, for box of 1.1 will be equal to 1. Let's study the next one. What about this? F of x is equals to -2.5. On the number line, this is your -1, this is -2, this is -3. So -2.5 would land somewhere around here. All the values which are less than -2.5 will be these on the left hand side. And if you consider -3 is the greatest amongst those negative values, so the value over here will be -3. You have to find the greatest integer, but integer which is less than the given value. So this is equals to -3. It can be either less than or equals to. If you have a number, directly write the number, because that number is equal to itself. Now, what about those infinite values of x? Let's consider the values from 0 to 1. If you place x is equals to 0, your y should be equal to 0, same value. If you place x is equals to 1, your y should be equal to 1. X is equals to 2, y is equals to 2, because for same value of x, you're getting the same value of y. If you're taking the values from x is equals to 0 to 0.9. For all these values, 0.1, 0.2, 0.3, the greatest integer less than or equal to x is 0. For 1 to 2, 1.1, even if in place of 1.1, if we would have placed 1.2, 1.3, you still would have ended up with 1. So from these values, 0 to 1, you're getting the value y as 1. Let me draw this a little clearly. So from 0 to 1, your y value is equals to 0. From 1 to 2, your y value is equals to 1. From 2 to 3, your y value is equals to 3. 4, you're getting a step kind of structure over here. Similarly, from 0 to minus 1, you'll always get minus 1. From 0 to minus 1, yeah, you'll always get minus 1. From minus 1 to minus 2, you'll get minus 2. From minus 2 to minus 3, your y value will be equals to minus 3, and so forth. Again, a step kind of structure. Amongst these steps, what about this? At x is equals to 0, you should get a value 0. At x is equals to 1, you should get a value 1. X is equals to 2, value 2. X is equals to 3, x is equals to 4, x is equals to 5. What about the other value? These points should be hollow. Which means at x is equals to 1 lies over here, because your y value is 1. X is equals to 1 over here. It cannot be placed over here, because in your graph that value represents y is equals to 0. For x is equals to 1, you should get y is equals to 1. Hence, the dot is placed over here. Hope this is understood. Let's calculate range. Domain itself is considered as real value, and codomain as, again, real value. Range is all these points, 0, 1, 2, 3, 4, 5, minus 1, minus 2, minus 3. So range are set of integers. You should get integers as range, hence greatest integer function. The range is integer values. Next. So this ends the different types of functions covered in your text. Now, there are other types of functions as well, like smallest integer function, CIF, or the value for smallest integer function would be something like smallest integer less than or equal to x. Then there are algebraic and exponential logarithmic functions, which we'll cover in 12th standard, probably chapter 5. There are other types of functions as well. As we understood, polynomial functions itself contains a lot of functions, but we will not study about those right now. We'll come up to the next topic, which is algebra of real functions. Now, to understand this topic is very simple, because you've been doing the same algebra. You've been working with functions for a while now. So you know how to divide two functions, you know how to add two functions or subtract two functions. You just do not know the theory behind it or the representation of it. So that we'll study here, as well as we'll study a few examples to just brush up the concepts. Addition of two real functions. Let us consider f of x as first function and g of x as second function. So you can simply add these two functions. So let's consider f of x is equals to 2x plus 1. and g of x is equals to 3x. So you can simply add them, f of x plus g of x, just like normal terms, and you'll end up with these two are like terms, so you can merge them out. You have 5x plus 1, the standard procedure that we've been doing since years now. In a combined sense, these can be written as f plus g in a bracket of x, pronounced as f plus g of x. So this means f of x plus g of x. Understand, both f of x and g of x have certain domains and range. So say f of x is equals colon f of x function. Since both have x as its independent variable, we will consider define for function f and for function g. They should point from a single domain to, say, R. And G should also point from a single domain, from the same domain to R. Both are defined for the same variable x. I should have written arrow. They are a subset of R, but it's an arrow. That's what it is in representation. Sorry. So function f points from x to R. Function f defined from set x to set R, and function g should also be defined from the same set x to R. For all these values, we'll consider this particular standard definition for f and g. In this case, x is a subset of R. It is additional piece of information or relation between your domain and codomain. Moving on. Subtraction of two real functions. We can consider the same values of f of x and g of x, and we can subtract them as such. So f of x minus g of x. That's how it's represented, f of x minus g of x, or you can combine them to say f minus g of x. First function as it is, minus second function. Since the second function is a single variable, single term, you can easily change the sign and write it like this. Like terms, after calculation, you'll get minus x plus 1. Next, multiplication of a real function with a scalar or real number. Let that scalar be alpha. So if the scalar is alpha, then alpha into function of x. This is multiplying a scalar with function. In a combined sense, it can be written as alpha f of x. Let us consider alpha is equals to 2. So alpha into f of x is equals to 2 into 2x plus 1, which is again something that we've already encountered before without knowing about it. So 4x plus 2. Multiplication of two real functions. Now, if you multiply two real functions, it's also called as point-wise multiplication. You'll get to know why. So multiplication of two real functions can be written as f of x into g of x. Let's consider the same functions f of x into g of x. This can be written as x plus 1 into 3x, which is 6x plus 3x, 6x squared plus 3x. Multiplying this first term with the first term plus multiplying second term with the first term, or using distributive property. If instead of g of x, we would have had h of x as, say, x plus 4. And now you're multiplying f of x with h of x. So binomial multiplied by binomial, 2x plus 1 multiplied by x plus 4. This is 2x squared plus 8x plus x plus 4. So 2x multiplied by first term x plus 2x multiplied by 4, which is 8x, plus 1 multiplied by x is x, and 1 multiplied by 4 is 4. This is 2x square plus 9x plus 4. So point-wise multiplication. 1 point multiplied by 1, 1 point multiplied by second point multiplied by first, second point multiplied by second. This is point-wise multiplication, multiplication between two real functions. Next, division of two functions. Let's consider the same functions, and we can write division of two functions as f of x upon g of x, provided the g of x is never equals to 0. So division of it can be written in combined form as f upon g of x, and the multiplication can be written as f into g of x. So division f of x upon g of x not equals to 0, division of two functions. This can be done by using division method. So you are dividing f of x by g of x. So f of x will be written inside 2x plus 1. This is 3x. You're dividing 2x plus 1 with gx, 3x. So a method says take the first value, 2x, first term, divided by the first term, which is 3x. X gets cancelled, left with 2 by 3, and here you have 3x. Subtract, and you get 2x, subtract, and you get the remainder as 1. So your quotient is 2x, 2 by 3, and this is your remainder. Or you can split it. Say 2x upon 3x plus 1 upon 3x. This isn't the answer. This is just rearranging them. You get the answer by actual division. In a simpler term, instead of 2, anyways, you get a quotient 2 by 3, you get a remainder. You can represent it in whatever form is required by you in that particular question. If remainder theorem is required, then dividend is equal to divisor into quotient plus remainder. That form can be self-explanatory. Anyways, this is the same as the division that we used to do of polynomials. So this ends this chapter of relations and functions, or the theory part of it. We'll continue with trigonometric functions in the next class. Thank you.